Okay, so this lesson is in chapter 7 of your text and it's leading us into nuclear fusion and nuclear fission. So the first part that's important, and I've put all the key things here circled in red so you can make notes of them in your book, is nuclear transformations. Now we've already talked actually quite a lot about nuclear transformations. It's all about transforming the nucleus of an atom, and alpha and beta decay are examples of that. So you have protons and neutrons changing. Remember we have protons and neutrons changing into electrons and positrons, for example, and then leaving behind a neutron or a proton that wasn't in the nucleus before. So we've actually seen this. But the interesting thing is that there are artificial nuclear transformations that have been created as well. And that's been done by basically bombarding or shooting particles at atoms, okay? So you can see here this example. This is by Ernest Rutherford, who's very famous in the world of physics, who fired alpha particles, so helium nuclei, at nitrogen atoms, and he was able to produce an isotope of oxygen. So what was cool about that is, artificially, he was able to take an element, nitrogen, and by using alpha particles, turn it into a completely different element, into oxygen. So this is where people were really excited, because it was like, maybe we can do this thing that was believed to be possible by alchemy, okay, which was to turn lead or metal into gold. In fact, fun fact, is that this is in Harry Potter and the Philosopher's Stone. So it was believed that the Philosopher's Stone was able to do this nuclear transformation. So I'll just play you this little bit.
Of course, here it is. Nicholas Flamel is the only known maker of the Philosopher's Stone.
The what?
Honestly, don't you two read? The Philosopher's Stone is a legendary substance with astonishing powers. It will transform any metal into pure gold and produces the elixir of life, which will make the drinker immortal.
Immortal?
It means you'll never die.
I know what it means.
So it's kind of cool, because now when you watch Harry Potter, you can think, wow, it's about nuclear transformation. So that was the idea, and it's a really long-standing idea that there was this substance that could turn metals into gold. So it is possible, but it's probably extremely expensive. Because in order for you to do these kinds of transformations artificially, you need to have amazing equipment to shoot these particles at atoms. So this is where we're looking at the building of particle accelerators. So in the early 1930s, they looked at shooting charged particles like protons and alpha particles at atoms. And the problem with this is it requires a lot of energy, because inside the nucleus, remember, we have little positive protons. There's my nucleus. So when we're shooting positively charged particles at this, we already have positives inside here. So you get this repulsion, and they're often sort of shot away. So what they found to overcome this is that they could use neutrons, which have no net charge, and they're able to enter the nucleus a lot more easily. So like my little neutral charge neutron, they can enter and split apart, or even cause other nuclear changes inside a nucleus. So both protons and neutrons are used today to produce radioisotopes, and there's different ones here to do with medicine or mining and other uses. So they're pretty important to our everyday life, actually. And particle accelerators are also used to produce new elements. Now often the elements that they produce have extraordinarily short half-lives. So for example, atomic number 118 was produced using particle acceleration, but they only lasted for 0.89 microseconds or milliseconds, and that was for their half-life. So they've actually all disappeared. So the ones that were created have disappeared. So we're trying, I guess, to use these particle accelerators to create isotopes or elements that are actually stable and have longer half-lives, so don't disappear. So I've got some examples here of some different particle accelerators. This one over here is in Switzerland. This is the particle accelerator CERN. So I'll just show you. This is the Large Hadron Collider. It's the world's most powerful particle accelerator. It is in Switzerland. It is a 27-kilometre ring of superconducting magnets. And the magnets, what they do is they hold these particles inside this loop and forces them round and round so that they build up energy, and then they smash them into things. They're kept in an ultra-high vacuum. They're electromagnets that are used. And you can see here the chilling that's required on the magnets is colder than outer space, negative 271.3 degrees C. So it's actually a facility that uses a lot of energy as well to do all of these things, to power the facility, to keep it cool. So it's really cool. If you're interested in that, type in Large Hadron Collider or CERN, Large Hadron Collider, and you can actually have a look. It's got the pictures and a little bit of information about how it works, which is really neat. And the other one that I want to show you is actually in Melbourne. There's something called the synchrotron in Melbourne. The synchrotron's a large machine about the size of a football field that accelerates electrons to almost the speed of light, and they're deflected through magnetic fields. And then they're channeled to workstations and they're used to do all sorts of things. So in the sciences, in mining, medical research. And this is actually here in Victoria and Melbourne by a group called ANSTO. So the synchrotron's really neat because it is being used for some really cutting edge science and something you might be interested in going into if you continue with your physics. So those are our particle accelerators, very big. Now the next part we're looking at here is the discovery of the structure of the atom. Now I've given you a sheet to stick into your book for this one. I just wanted to talk you through a little bit of what's on the sheet. So the first pictures A and B are about the discovery of the nucleus. And this was done by Geiger and Marsden, who were two people who worked with Ernest Rutherford, who again is a name that keeps popping up. And basically what they did was they shot alpha particles. And remember that alpha particles are helium nuclei. And remember that they're 2+ charged as well, because they don't have the electrons to counter those 2 protons. So these are positive particles that are being shot into the gold foil. And what they discovered was that these positive particles bounced off. They were bounced off because they were being deflected by something, and it was this positive charge that was inside the atoms that make up the gold foil. And what Rutherford found was in order for these deflections to happen at the angles they were happening at, the positive charges had to be concentrated in a very small area, which he called the nucleus. So he knew there were positive charges in there. And so he basically figured out this idea that you have the little nucleus and then you've got the electrons spinning around. And in the nucleus you've got some positive protons that are deflecting the alpha particles. They knew also that there was something else going on inside this nucleus, and to discover what that was, they found these unknown particles by shooting alpha particles again. This is another fellow, James Chadwick, shooting alpha particles at beryllium, and then finding these unknown particles that were bouncing off. They didn't know what they were, but then they were getting protons when these unknown particles were hitting paraffin wax. And they figured out through some different experimentation that these unknown particles were actually neutrally charged. They were neutrons. And what was happening was the neutrons were hitting the wax and protons were being pushed out into the chamber that was detecting them. So there were 2 different experiments that actually discovered the 2 things that make up the nucleus. So one found the protons and figured out that they're inside a very small area. The second experiment, this one down here, which is experiment C, found that there were also these neutral particles, the neutrons. So in terms of the stability of nuclei, now again, remember the red things are important. There's quite a lot of red stuff here that's important, but it's because we're now looking at why do nuclei stay together? Like, why don't all of these neutrons and protons and electrons just fly apart? Well, there's a lot of things holding them together. The first thing is I'm going to draw a picture. I know my pictures are a little bit dodgy, but I'm just going to do this one as a 4-2 helium with a couple of little electrons. Okay, so if we think about what's going on here, we've got some positives inside here, some neutrals and some negatives. Now the first thing that's keeping the electrons around the nucleus is what's called the electrostatic force. And the electrostatic force acts between opposite charges. Okay, so that's keeping that together. Now the stability of the nuclei inside this atom actually depends on 2 things, the protons and the neutrons, but the number of neutrons to protons, that is the ratio of neutrons to protons. And it says here in this box, for small nuclei to be stable, the number of protons must be roughly equal to the number of electrons. So check this out. early on when we have small atoms, this is the number of protons, number of neutrons. And can you see here when you have 6 protons, 6 neutrons, can you see there that there's a black line that runs through this graph? Anything that's on a black line is a stable isotope. Anything that's a red or green area is an unstable isotope. So you can see there 6 and 6 is pretty stable. Let's look at 14. 14 and 14, that's on the black line, that's pretty stable. But let's look at what happens 28. You're not on this black line anymore. This is actually an unstable isotope. And the reason for that is that as the number of protons increases, you actually need more neutrons to remain stable. So check this out. When we get to, for example, 82 protons, if we follow up, we don't hit the black line of stability, this one here, until here. And that is at 126 neutrons. So for 82 protons, you need 126, you need like half again as many neutrons to hold that thing together. And the reason for that is this thing that is called the strong nuclear force. So the idea is that when you have all these protons inside a really, really close area, the protons actually repel each other when they're brought together. But we have a force that is actually able to overcome that repulsion. And I'm just going to highlight one other line here. And that force that overcomes the repulsion is the strong nuclear force. And the pull of the strong nuclear force is much greater than the push of the protons acting against each other. So that's what keeps it together. And this strong nuclear force is to do with our neutrons. It's really important too to understand why this diagram looks the way it does. Now we've got two sections, a red and a green. Now the red section is any isotopes that decay by beta minus decay. And so for example, let's pretend we're here. Can you see that we're a bit above this black stability line? And that's because at this point we actually have too many neutrons. You're a little bit too high. Now remember that beta minus decay is where you have a neutron, so 0, 1, that turns into a proton and an electron. Now what happens is if you have beta minus decay, you're losing neutrons. They turn into protons, and that helps you to go down back towards the area of stability because you're actually losing neutrons. You're also actually going across this way at the same time because you're gaining protons. So that helps you to move basically in this direction closer to the stability line. So you can imagine now or understand that if you're on this side of the line, so let's pretend something over here, we've now got too many protons. So we're a little bit too low, but below our stability here. So this is where we have beta plus. So beta plus decay is where you have a proton which decays into a neutron and a little positron. So this is where you're gaining neutrons. So that helps you to go up. And as well as that, you're losing protons, which means you go back that way. So overall, you're moving in towards this black stability line by that type of decay. So that's why we actually have those two types, different types of decay. They're types of decay that help us to get closer to this stability line for our isotopes, our radioisotopes. So that's why this is a really interesting diagram to understand why it works. All right. Nucleus changing is to do with something called the weak nuclear force. So we've talked about strong nuclear force, which holds everything together. The weak nuclear force is used to explain the transformation of neutrons into protons or the other way around, so to do with beta minus and plus decay. But the weak nuclear force is very tiny, 1/1,000,000th that of the strong force. So that's why the whole thing doesn't fall apart, only a little part of it is going to decay. So the rest of the nucleus is held together by the strong nuclear force. You can see here that the strength of the strong nuclear force in this table, it's from your physics book, is really, really strong. It's a strength of 1. All of these are fractions of 1. So electric and magnetic, 1/137, so a fraction of the strength of the strong nuclear. Weak nuclear is 1/1,000,000th of the strength, and gravity is a lot less than strong nuclear force. And that makes sense, right? Because if this is strong, this holds everything together. It holds atoms together. It holds our world together. Gravity, we can overcome gravity. We can fly. We can jump. Okay, we can, lift our hand off the desk. So gravity is not that strong, but the range is different. So gravity is everywhere on Earth, whereas the strong nuclear force only happens in a very, 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 very small diameter of a nucleus. Okay, and all of these are attractive forces except magnetic and electric, because they can also be repulsive if you have same charges or same polarities on magnets. All right, last section today is just looking at binding energy. Now this leads us into nuclear fusion and fission in our next lesson. It's all about the energy required to bind or split a nucleus. So the amount of energy needed to overcome the strong nuclear force and to split or pull apart a nucleus is called binding energy. It's really important. Now it's the amount of energy that has to be added to the nucleus to split it apart. So if you've got a really happy little, let's call this neutrons and protons and an electron, a happy little hydrogen 1, 2 sitting here. If we want to split this apart, the energy that we have to put into here is quite large, okay, and this is the binding energy. That's going to split this up, okay. When we think about the energy that's used, we measure it in what we call electron volts, and in particular mega electron volts. So I know in a past video we talked about energy. If you haven't written down this part down here, really important that you know about mega electron volts. So when we look at what an electron volt is, it's very small, okay, but energies of nuclearation are usually between 0.1 to 10 mega electron volts. 1 mega electron volt is this much energy, 1.602 by 10 to the negative 13 joules. So it seems small, but when we explore it a little bit more, you have to think, well, you don't just split one hydrogen, you're splitting an amount of hydrogen. Think about how many hydrogen atoms are in, like, a kilo. And that's thinking of things like uranium, splitting uranium. When you think about nuclear weapons or nuclear fusion and fission reactions, you're doing that to a mass of uranium. So when you add up all of this energy in each atom, that's where you get big numbers. Okay. This particular graph here is a graph of binding energy versus mass number. Now can you see here that early on the small mass numbers, that's like hydrogen, helium, lithium, beryllium, the small guys, they have smaller binding energies per nucleon, and a nucleon is a component of the nucleus, so a neutron or a proton. So they're quite small. But as you go along here, so as you get bigger, you start to peak. And so you sort of peak just under 9 mega electron volts, which actually is done by iron. Fe is iron. Iron has the highest binding energy, which means that it is actually the hardest to split apart. That means it's also got the most stable nucleus. And you can see as you continue down, these guys are still quite stable. Uranium is still reasonably high, so about maybe 7.5 mega electron volts. But the fact that uranium's binding energy is so high is why when we split and use uranium in nuclear power, we get so much energy out. A lot more energy than if we were to do it with, helium. So in our next lesson, we're going to actually look at the specific energies of binding for both fusion and fission of a nucleus. But for now, it's just enough to make sure that you understand what binding energy is and to understand the scale. So maybe a little quick sketch of that might be good to put in your book as well.